So let's have some examples on the electronic configuration. So let's say the question is draw the electronic configuration of sodium. So the first thing that you do is go to the periodic table and check the atomic number of sodium, where the sodium is. This is not the mass number, the atomic number. So you always need the atomic number. Why do you need the atomic number? Because remember what we said, that the atomic number is equal to the number of electrons in case sodium is a neutral element. And here it is a neutral element because it doesn't have a zero charge. It's neither positive nor negative. So sodium over here has 11 electrons. So this one is the number of electrons. Okay, so we say that sodium over here, it does have 11 electrons, which is the atomic number. So now I want to go ahead and distribute those 11 electrons in the subshells and in the shells, in the subshells, and in the orbitals. So we're going to start by, I know that this is the sequence. And to get this sequence, you guys, again, you would need to draw this orientation in there and go ahead and write down the sequence based on this orientation. So we're going to end up with this sequence here, okay? So sodium 11, so I need 11 electrons, right? So these are the 11 electrons in there. This is 10. So from the S, I need just one. So if I want to draw the electronic configuration, I'm going to start with the 1s2, the 2s2, and the 2p6, right? This is 10 electrons so far. And then I just need one more because I have a total of 11 electrons. So I just need one more, which is the 3s1, not 2. So I need 3s in there, and I need just one electron in the s, and that will be a total of 11 electrons. So now if I look at the subshells in there, I would see that the s orbital is completely filled. So this is going to be the k shell. This is n equal to 1 shell, which is the k shell that is completely filled. The s shell, the n equal to 2, has the s and the p. So the s and the p are completely filled as well because the s has 2 electrons, the p has 6 electrons. So these are completely filled as well. And this is considered to be the L shell, and this is n equal to 2. Okay. I always target the shell that is not completely filled, because the shell that is not completely filled is the outermost shell. So think about it like this. You do have your nucleus in there, and around the nucleus for the sodium, what do we have? We have n equal 1, n equal 2, and n equal to 3. Now the n equal to 3 has one electron in it, n equal to 1, so this is going to be the nucleus. And then we're going to have the first shell, which is n equal to 1. I'm just going to draw it as an elliptical one. So that is going to be the n equal to 1 shell. And then we have the n equal to 2 shell here. This is the n equal to 2. And then we have the n equal to 3. And that is equal the n equal to 3 there. Okay? Let's put the n equal to 2 over here. So that is the n equal to 2. This is the electrons of the sodium. So sodium has 11 electrons. In the first n equal to 1, you do have the s orbital in there that has 2 electrons. This is completely filled. So n equal to 1 has 2 electrons. This is 1 and this is 2. You can draw them anywhere in the n equal to 1. Honestly, it doesn't matter in there. So here I know and see that the n equal to 1 is the shell which is the closest to the nucleus. And this shell does have 2 electrons in it. This orbital does have 2 electrons in it. Okay, this is the n equal to shell. No, n equal to 1 shell. The n equal to 2 shell has what? It has the s orbital in it, and it has the p orbital in it. Okay, so it has the sp. This is n equal to 2. The s has 2 electrons, and the p has 6 electrons. So the total number of electrons is 8. So the n equal to 2 has 8 electrons. Let's draw the 8 electrons. So this is going to be 1. This is 2. Just to draw them anywhere, just make sure that they are 8. 4, 5, 6, 7, and 8. So the n equal to 2 has 8 electrons in there. And then the last shell, this is the outermost shell. Remember when we defined the valence electrons and we said these are the outermost shell? You guys, the outermost shell is the last shell that is not completely filled, or it is the last shell in there. Okay, this is the last shell for that particular atom. It just varies from one atom to the other. For the sodium, the last shell is N equal to 3. And the last shell, see how many electrons does it have? It has just one electron. Just one electron in there. What defines where sodium is that last shell. So since the last shell has one electron, this is equivalent to the group number. So we say that the valence electron for the sodium is equal to 1. Okay, so over here, the valence electron of sodium, this is equivalent. This is the valence. We call it the valence electron shell for sodium. For sodium, and this is representing the outermost shell, which is equivalent to the group number. So this is why we say that sodium has one electron in its outermost shell, so sodium is in a group number 1. If it had 2 electrons, then it will be in a group number 2. Okay, let's have another example. Aluminum. So it's not always you need to draw this, but I'm just drawing it just to make you understand what does these shells and subshells mean. Okay, so back to this one. So the n equal to 1 contains has the s orbital. So this one has the s orbital. The n equal to 2 has both. It does have the s and the p orbital, and the n equal to 3 has the s orbital in there. For aluminum, I need 13 electrons. Go to the periodic table. Aluminum is a 0 charge, so that is going to be a 13 atomic number, which is equivalent to the number of electrons. It's the number of protons and the number of electrons. So this 13 in here is the number of electrons. So now I have to distribute those electrons in the orbitals. So I'm going to start with the same sequence in there, okay? So that is the same sequence. I need now 13 electrons. So that is the 3s1, and now I need just one electron from the p. So it's going to be 1s2, 2s2, 2p6, 3s2 in there, and then 3p1. If you count those, this is a total of 13 electrons. This is 10, 12, and then 13. So let's go ahead and arrange those in shells, okay? So we do have the n equal to 1 shell, which is completely filled. This is the K shell. We have n equal to 2, which is completely filled. Normally, the reason why I like to rule those out of the way, because these are completely filled, so they have nothing to do with the valence electrons. And then coming to the outermost shell, which is n equal to 3. This is the last shell in there. The last shell is not completely filled. So what I do is I look at the number of electrons in this shell in here, and I see that, okay, I do have here 3 valence electrons. Remember, we called the electrons in the outermost shell valence electrons. So that's why I'm calling those 3 valence electrons. So this is why we say that aluminum is in group number 3. Okay? Note that every shell from n equal to 1 to n equal to 7 has a capacity of 2n squared electrons, where n is the shell number from 1 to 7. So if you are working with n equal to 1, then in this case, the n equal to 1 shell has a capacity of 2 electrons. If you have n equal to 2, then the shell has a capacity, n equal to 2 shell has a capacity of 8 electrons, 18, n equal to 4 can fit up to 32 electrons, and so forth. Let's have another example. So for sulfur 16, I wrote down the electronic configuration for the sulfur. This is 10, 12, 16. So you do have 16 electrons in there. I stopped at the 3p4. Still, n equal to 3 is not completely filled. So we do have the K shell, which is completely filled. This is n equal to 1. We do have the L shell, which is completely filled, n equal to 2. So n equal to 3, this is the outermost shell for sulfur in there. So whatever electrons you have in n equal to 3, those are going to correspond to the valence electrons. So you can easily see here we do have 6 valence electrons for sulfur, and this is why sulfur is in a group 6. Okay. Let's say, for example, if we want to draw the orbitals and show the electron distribution. So if we want to draw the orbitals and show the electron distribution, normally we do this for the outermost shell, which is the shell that is not completely filled. So to draw the orbitals, we draw the s orbital here, which we know that it is made up of just one subshell. And we draw the p orbital and the p subshell, which is made up of 3 orbitals. So the s subshell is made up of 1 orbital, the p subshell is made up of 3 orbitals, 3 p orbitals are there. So the s subshell has a capacity of 2 electrons. We say that this one is completely filled. So that is the s, and that is completely filled in there. Now for the p, I want to go ahead and fill the electrons. So I have 4. Remember how we filled them earlier. So you fill the 3 there, and then whatever is left, you go back and you fill it. So this is going to be the 4th. We have the 3px, this is the 3py, and that is the 3pz. So if you look at the 3py and the 3pz, the 3py and the 3pz, these have just one electron in the orbital. So these are considered to be unpaired. Unpaired is a term that we use whenever the orbital has one electron. So it means that it's one electron in each orbital. And then the S and the 3px, those are paired, meaning these are considered to be paired electrons, meaning that you have 2 electrons in each orbital. Okay? So you have the K shell, the L shell, and then we forgot to mention that this one is the M shell. The M shell is not completely filled, so this one is going to correspond to the valence electrons, which is the group number of the atom. We can use the periodic table, you guys, to use the electronic configuration. We're going to skip the lanthanides and the actinides. The F series is the lanthanides and the actinides. It's here. But we're going to go ahead and skip those. We do have the S block, we have the D block, we have the P block, and we have the F block in there. So the S block is made up of a group 1 and the group number 2. So any element in the group 1 and the group number 2 is going to end up in the S. So it's either going to end up in the S1 or it's going to end up in the S2. So for example, if I have beryllium in there, Be, okay? So beryllium is going to end up in 2s2 because the S has 2 electrons, it's 1 in each. So it's going to be 2s2 there. You do have the D block, and the D block has 10 electrons, right? So each one of these is going to be an electron. So if you have an element in here, this element is going to end in 3d9. Same thing, an element in here is going to end up in 4d9. An element in here is going to end up in 5d2. And then you have the P block. The P block has 6 electrons, and these are the 6 blocks there. So an element in here is going to end in 2p2. Okay. An element in here is going to end up in 5p2, and an element in here is going to end up in 5p5 as well. So you can easily read the electronic configuration from the periodic table. So let's say, for example, if I want, let me make this a little bit bigger. Okay, so if I want the electronic configuration of, write down the electronic configuration of carbon. Okay, so let's write down the electronic configuration of carbon in there. So we're going to start by reading from here. So we're going to start with 1s. It's not going to be s1 because it's going to be 1s2. So this is 1s2. If I draw it, this is carbon. Carbon is going to be 6, right? It does have the atomic number of 6. So it's going to be 1s2, 2s2, and 2p. Um, 2p, this is going to be 2. So 1s2, 2s2, and 2p, 2 in there. So let's go ahead and read it. It's 1s2. So this is the 1s, this is the 1s2. So it's going to be 1s2. It's going to be 2s2 and 2p and a 2. So because this is the p block and the carbon ends in here, so it's going to be the 2p2. So carbon ends in 2s2 and 2p2. This is the electronic configuration. The n equal to 1 is completely filled. This is the K shell, and the L shell is not. This is why, if you take a look, carbon has 4 valence electrons. It is in a group number 4 because its outermost shell is made up of 4 electrons. So let's say, for example, we want to read the electronic configuration of calcium. Calcium is 20. So we're going to start with 1s2, 2s2, 2p6. Okay, this is all 2p, and it's going to be 6. We need it all. 3s2, 3p6. Again, we need all of that. And then coming here, we only need the 4s2. That's it. We stop. So calcium ends in 4s2. Let's say if we want to read the electronic configuration of Sr. So Sr has an atomic number of 38. Okay, we can read it from the periodic table, and then we're gonna go ahead and write it down. So Sr starts with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Um, this is the D block. It starts with the D. So this is, I need all of that. This is 3D10. And then this is 4P and 6. And this is 5S2. I'm just going to stop here at the SR. So let's write that down. So SR has an electronic configuration. This is atomic number of 38. So SR is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and then the last shell is going to be the 5, the n equal to 5, the 5s2 in there. So the n equal to 5 is the last, it's the outermost shell, and it does have 2 electrons here. So this means that this is the valence electrons of the strontium, and it is group number 2. Okay, you are not responsible to read the lanthanides and the actinides and their configuration from the periodic table. So lanthanides and actinides, we're not going to talk about those. What I want you to focus on is the is the P block, and we're going to talk about the D block in a moment. So there is an abbreviation when you want to draw the electronic configuration, because as you can see over here, I mean, if you are working with elements in the periodic table, the electronic configuration can be very long. So in order to abbreviate the electronic configuration, we relate it to the noble gases. So instead of saying, or instead of writing the electronic configuration of everything that is here, let's say, for example, if you want to write the electronic configuration of Sr again, okay? I relate this to the electronic configuration of the noble gas before it, which is the krypton. So krypton has a simple atomic number of 36, right? So I would say that, okay, everything in here, this is 6. So everything in here relates to the configuration of the krypton. This is how I do it, okay? So everything here is the configuration of a krypton, and then whatever is left is basically the 5s2, so you just write it as a 5s2. It's kind of like an abbreviation. Instead of drawing the whole electronic configuration, you stop at the nearest noble gas, and then you continue afterwards. Let's have another example. Okay, so for example, phosphorus 15. If you want to draw the full electronic configuration, this is the full electronic configuration. It does have 15 electrons. Okay, so phosphorus has 15. This is the number of electrons in here. So this has 15 electrons, which is the same as the atomic number, because remember, phosphorus is a zero charge, so the atomic number is same as the number of electrons, the same as the number of protons. So it's 15. So it's going to be 1s2, 2s2, 2p6, 3s2, and 3p6 in there. Remember that phosphorus is in a group number 5, so this is why the valence electrons are 5 over here. Okay, if I want to go ahead and relate this to a noble gas configuration, then if you look at phosphorus at the periodic table, where's phosphorus? So phosphorus is here in the periodic table. Okay, so this is phosphorus in the periodic table. The nearest noble gas is neon, and it is 10. So I'm just going to skip all the electronic configuration that is before neon, and that is 10. So I come over here, and I would say, okay, the first 10 over here, this is the electronic configuration of neon, Ne. So I would say that now the noble gas electronic configuration of phosphorus is going to be neon, and then whatever is left, which is the 3s2 and the 3p3. This is called the noble gas electronic configuration, and it is an abbreviated way in order to draw the electronic configuration of elements. Same thing for potassium. For potassium, this whole thing is the same as the configuration of argon, not krypton. It's the same thing as the configuration of argon. So I would say that potassium has the same as argon configuration in addition to 4s1. Iron is the same thing in there. So all of those until the 3p6, until 3p6 here. So this is also the same as the electronic configuration of argon. And then I do have the 4s2 and the 3d10. So this is the electronic configuration of iron, which is drawn as a noble gas configuration. This is a 3d6. Okay, now let's consider the transition elements and their electronic configuration. So transition elements, what are they? If we look up here, the transition elements are the D block. So you have the S block, you have the P block in there, and then you have the D block. The D block is specifically for transition elements. So all transition elements, they end up in the D orbital. Okay. There is an exception with the transition elements, that always you need to empty the s orbital to fill the d orbital with the transition elements. Let me show you what I mean. So iron 26, we're going to go ahead and draw the electronic configuration for iron, and that is equal to 1s2, 2s2, 2p6. So we're going to fit all the 26 electrons in there for the iron. So iron here has 26 electrons. We're going to fit it all in here. That is the 3s2, 3p6, 4s2, and the 3d10. Now, whatever 3d, actually it's not 10 because I just need 6. So it's going to be 3d6 in there. Okay. So if you look at iron in the periodic table, where's that? This is iron in the periodic table. It is made up of 3d6 in there and 4s2. So it's 4s2 and the 3D6. This is specifically for transition elements. So you are not going to apply this for regular metals, just for transition metals. Okay. So for transition metals, what I want you to do is arrange the n equal 1, n equal 2, n equal 3 together, n equal 4 together. So we're going to start with the 1s2. This is the n equal to 1 shell, the n equal to 2, 2p6. This is n equal to 2. N equal to 3 is 3s2, 3p6, and 3d6. This is n equal to 3. So it's going to be the 3s2, the 3p6, and the 3d6 in there. Okay, so that is equal to n equal to 3. And then n equal to 4 is the 4s2. That is n equal to 4. And again, you only do this for transition metals. So for transition metals, draw their electronic configuration first, and then arrange the electronic configuration in the shells, n equal 1 and 2, n equal to 3, and n equal to 4, etc. And then apply this rule in here. That is only used for transition metals. See, when you look at the subshells, the S, the P, the D, and the F. The F is the highest energy subshell, and the S is the lowest energy subshell. Okay, so for the transition metals, because they are D block, we always empty the S to fill the D. So you empty the S to fill the D. So over here, the D has 6 electrons. So it still has a capacity of accepting more electrons, because I know that the total number of electrons for the D is 10 electrons. So what you do over here is that you empty the s orbital to fill the d, and you can fill it to the max. So here you go. So empty the s. So we're going to go ahead and we're going to empty the s orbital, and we're going to fill the d. So to fill the d orbital in there. Okay, so empty the s to fill the d. Now the electronic configuration, it is going to be 3d8 and 4s0. We emptied all the s, so we took the electrons from the s. And why did we take electrons from the s? Because the s is the outermost shell. It's the last shell. So we took the electrons from this shell and we added those to the d. We have the room for these electrons. If you don't have the room, you cannot do it. But we have the room over here because we still, the d is not completely filled yet. So this is going to be the electronic configuration. So if we want to draw the electronic configuration of iron, now it's going to be 1s2. Let's draw the 1s2 in a better way. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d8, and then 4s0. So that is going to be the electronic configuration for iron. So always in transition metals, we are going to empty the s orbital to fill the d orbital, because the transition metals always prefer their d orbital to be filled. Let's have another example, which is silver. Silver is a transition metal, okay? So if it's a transition metal, let's go ahead and draw its normal electronic configuration first, and then arrange the shells into n equal 1, n equal 2, n equal 3, and see if we can empty the s orbitals in there in the outermost shell to fill the d orbital. So here you go. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and 4d9. Okay, is that it for the 9? And this is going to be 10, 20, 30, 38, and 9. This is 47. Okay, great. This is 47. Now, after you do this, we're going to go ahead and arrange in in subshells or in shells n equal to 1, n equal to 2, in shells. Arranging the n equal to 3, this is the 3s2, 3p6, and the 3d10. So this is n equal to 3. And then we do have the n equal to 4. So here you go. These are the 4 orbitals. It's going to be the s orbital, the p, and the d. It's 9. And then the last one is going to be the 5s2. The 5s2 is the outermost. So that is going to be the 5s2 in there. We can easily empty the s to fill the d, but we don't want to empty all the s because that is going to be over the capacity of the d. The capacity of the d is only 10 electrons, so you cannot exceed that. So we just need 1 electron from the s to fill it with the d, and now it's going to end up in 4d10 and 5s1. Okay, so if we want to draw the electronic configuration of Ag, then that is going to be 1s2, 2s2, 2p6, 3s2, 3p6. You can put all the threes together, it's not a big deal. And then 4s2, 4p6, 4d10, and then 5s1. This is the electronic configuration of silver. Okay, so always remember transition elements. You have to arrange the shells into n equal 1, n equal 2, n equal to 3, and then empty the s orbital. Always empty the s shell or the s orbital in order to fill the d orbital. So empty the s to fill the d orbital. Cobalt 27, that is 1s2, 2s2, 2p6, 3s2. So far I have 12 electrons, 3p6, 4s2, and the 3d and the 7. Okay, so this is already arranged. We're gonna put the n equal to 3 together, so it's 3s2, 3p6, and the 3d7, and then we have the 4s2 in there. We can go ahead and empty the s and fill all the d, so that will result in 3d9 and 4s0. You can either put 4s0 or take the 4s. You don't even to mention the 4s. So simply it's going to end in 3d9. But the reason why I put the 4s0 just to show that I took electrons from the 4s was there. Electrons in the 4s were there, but I took those electrons in order to fill the d orbital of the transition metal.